This is going. We're rocking and rolling. Good. Okay. Tree diagrams. You guys get a little reminder of intro stats every time we start? How about? Now, don't be too mad at me because I was not able to make a new lab for today. So for the lab session today, you can just have time to work on, because I think you've got another lab due and an assignment. So you can just work on those for that time. How about, we'll give you another one. I'll save that for next Monday, but that'll be more to prepare you for the test. And so this Monday will be kind of like a makeup day. I got emails. I think I got emails from everyone. Sorry, I didn't reply. I just, before I got on my flight, I was like, oh, okay, good, nice. Okay, great, thank you. Yep, okay, good. So, thank you. All right. Yeah. Might fall asleep in the sun here. I know, it's not very good on there. Can you guys see? Oh, bless you. Yeah, is that better? Maybe we'll have to do this. Wait. All right. Now it's really nice and dark in here. Okay. So, where did we end off? Oh yeah, we talked about the variance inflation factor in the car package. So for a quick review, there's a VIF command. Oh shoot, what does it take? Let's just do it like that. I think it just takes the data set, but it's in the car package. So you'd have to install the car package, but then you can use the VIF, and I'm drawing a blank on what it takes, but it'll tell you what it takes, so it's no big deal. Okay. So the variance inflation factor was, we said that a VIF greater than 5 is an indication of multicollinearity, right? That there's correlation between one or more of these predictors, or I guess 2 or more, because that's how correlations behave. So it's an indication of multicollinearity. Yikes. And one thing that we emphasized and that we'll come back to today, because it's going to come back to haunt us, is that, okay, multicollinearity, that's fine. We can build a model that has multicollinearity. It's not something that we need to be afraid of, but it is something that we need to be aware of, right? And so it's multicollinearity means that there's some relationship between these predictors. And so when we interpret these predictors, right, the coefficients of each of the predictors, we're not going to be able to interpret them properly, right? Because they're going to be changing with the other predictors. And so if there is multicollinearity, we need to be careful. Oops. We need to be careful when interpreting the coefficients and their t-tests, right, to see if they're significant or not, because they're going to be related to other predictors. Coefficients and their t-tests because they will be related to the other predictors. So it's kind of this weird thing that we said, okay, well, we're not scared of multicollinearity, right? We're going to check the variance inflation factors, right? But we don't have to do anything if it's there. It just means that we have to be careful in interpreting our coefficients, because the coefficients are meant to be interpreted on their own, holding everything else steady. But if things are moving together and you can't hold one thing steady, then you can't interpret them the way that we usually would. So that's just something to keep in mind. And like I said, that's going to come back later on today, where that's something that we have to keep in mind. We didn't quite wrap up chapter 3, but that's kind of the main stuff that we talked about last day. Well, we led up to the variance inflation factor, but that was kind of the heavy hitter, so to speak. So in section 3.6, we're talking about testing subsets of predictors. And so everything that we're talking about is just trying to build a better and better model, right? Different techniques that we have, different things that we can look at, right? And so we're going to talk more about that today, just different techniques that we can have in our toolkit. And we're not going to talk about the case study, but I do think it's really, really helpful. Section 3.7 is all about a case study, which has data on retail clothing, and they're predicting how much someone is going to spend in the store, depending on how much they've spent in the past 12 months and how many times they've shopped there in the past 12 months, right? So kind of relevant data, right? Market information. And so, and they just kind of talk you through how they build their model, right? How they're going to try to figure out what their best model is, given the tools that we have so far. And so 3.7 is really good. It's just a case study. So I do recommend that you read it, but we're not, besides me telling you that it's really good and informative, we're not going to talk about it. So, we've seen individual t-tests, right? For each of the individual predictors, right? Is this predictor significant? Yes or no? Is this predictor significant? Yes or no? It does assume that there's no multicollinearity, right? And so it is assuming that we can hold all the others steady, right? That kind of thing. And we've also seen just an overall ANOVA, right? The ANOVA just has a look from way up above and says, hey, is there something going on in here? Yes or no, right? Am I able to use any of these predictors to predict my response? Yes or no? What we can do is we can go a little bit finer, right, between those two, because we're talking about individual predictors, right? That's very nitty gritty, or just the big overview ANOVA. Now we can say, okay, well, what if I want to test just a subset of these predictors, right? What if I think that some of these predictors are going to be acting as a cluster, right, and kind of behaving the same way, and maybe one of them is going to be able to replace, you know, 3 or 4 of them, right? And so now we're talking about just testing subsets of predictors. And so we have seen individual t-tests. for regression predictors, to determine if a single predictor is significant, if a single predictor is significant, we have also seen just an overall ANOVA we have also seen an overall ANOVA for regression to determine if any of the predictors will help in predicting the response. To determine if any of the predictors will help, I'll say, in modeling the response. In modeling the response. To see something kind of in between the two, right? To test a subset of predictors, right? We can use a nested F-test. And so to test a subset of predictors, we can use a nested F-test. Usually how this is going to come about is if I've got a kind of a complex model, but I suspect that a simpler version of it is going to do the same thing, right? Then I want to be able to compare those, and how I'm going to do that is with the nested F-test. And so if we have a complex model that we want to compare to a simpler version of the model, we will use the nested F-test. A key is that the simpler model has to be nested inside the more complex model. So that's the hiccup, right? And so the simpler model must be nested inside the more complex model. Drawing off of the models that we talked about last day, we talked about a complete second order model. Complete second order model looks like y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x1 squared plus beta 4 x2 squared plus beta 5 with the interaction term x1 x2 And I can throw the error term on there if I want. Sometimes I ignore it. Often I'll ignore it because I do find it's supposed to be there, obviously, but if you leave it off, I'm okay with it. I know I'm not supposed to, but because we're just starting, right? I just want you to focus on the model, right? We know that the model is just a model, right? There's just gonna be error. So in here, if we're talking about just beta naught plus beta 1 x1 beta 2 x2, and then the interaction term here, if we combine these, right, cutting out those squares, then we have the interaction model is nested inside here. And I think we touched on that last day, but I can't quite remember. So here, the interaction model is nested. So like I said, the key is that the smaller model has to be inside the more complex model, right? We can't compare half of a model with a half of a model. It just doesn't work. The textbook goes through and shows you all the calculations, but for us, if you want to run a nested f-test, you just use the ANOVA command in R, and it just has ANOVA of model 1, comma model 2, okay, where one of those is nested inside the other, right? It does assume that one of them is nested inside the other. And so in R, you're gonna use ANOVA and then model 1, comma model 2. Let's see if I can find that output. Oh, probably way back here. Oh. Wait. What?
We are just talking our way.
Oh. Okay. Okay. Let's see here. Here, this looks like one. Yeah. I have a note to myself that you could replicate this in the lab, but did I see deal? I don't know what page this is from. Doesn't say. Did it say?
On the side.
Ooh, nice. 374. Is that true? I don't want to lead you astray. I don't think that's true. It's fake. Fake news. It should be around page 130. Because there's no label on it. But that's where I'm stealing that from. So here, I don't really care what we're talking about, right? Which model we're talking about. I think this is the NFL data, right? But we're comparing just a simple model of points against plus yards against, right? And then versus the more complex model of points for plus points against plus yards for plus yards against plus TDs, which I'm assuming are touchdowns. Okay. So now, right, what I'm looking at is, okay, well, points against and yards against, am I able to pull that out essentially? Or am I able to replace them with maybe something simpler? How are they behaving as a group? Because they're both against variables, right? So it's not that weird that we could maybe pull them out as a group, but it seems like we need them both in there because we've got a significant f-test.
Oh, this is a nova, right?
It is.
Nova. So I'm just trying to understand the table. So 1 and 2 represents model 1 and 2. Right?
That's right.
Then the degrees of freedom are the sample size.
Yes.
Oh, the number of observations.
It's the number of observations minus the number of predicted predictors, right? Yeah.
Now the f-test is 11, which is translates to a very small number, which is says one of them is significantly different.
It's contributing significantly. And so here, I'll steal the other blurb too, how about? Because I think it's, here I even had a star by it.
Yeah, but you're comparing models.
Yeah, so here because I always find it's easier if you know what the null hypothesis is, right? And so here for the nested f-test, the null hypothesis is going to be that all the predictors in the subset can be removed essentially, right? And so what we're seeing here is, okay, well, I'm saying, or I'm thinking, or what I'm testing is, can I just remove these and still have a pretty good model, right? Like, can I live without the points against and the yards against as a group? Because it's only talking about in the subset. Right, so here, this is our subset, and so it's just setting, just like the overall f-test, right, is saying, hey, are there any coefficients out here that are not 0? Right, that would give you a significant f-test. And so here, now we're saying, okay, well, for these subsets, could I set them equal to 0 in here and still get a pretty reasonable model? And so when I'm rejecting that, I'm saying that at least one of those predictors in the subset is going to be significant. So I'll put a little note here. Wait, whoops. Because what this is saying is that at least one of the predictors in the subset is contributing to the model. They're all contributing, but contributing significantly is what I mean.
Because he arranged it the other way around here. So based on this equation, so you are trying to compare, to do f-test to the full model versus the reduced, correct? Or not the other way around. You accept this model, you remove weighted.
Yeah, instead of, so what it's doing is it's saying that the other guys, so the ones that aren't in the subset, right? So here, this is our subset, right? Just so we're all on the same page. So the ones that aren't in the subset are allowed to not be 0, right? Whereas in an overall f-test, we're just seeing, hey, are any of these guys 0, right? Or we're assuming they're all 0 until we have proof otherwise, right? And so now we're saying, okay, well, instead of just looking at each of these individually, I'm just saying, well, the other ones, they're allowed to have coefficients. But now I want to focus on these, the subset. Do they have coefficients of 0, yes or no? As a group.
It doesn't matter even if they have slope individually.
That's right.
Doesn't matter. If as a group they are 0, they are
Yeah.
accepting, then you're going to remove those two variables.
Yeah, because what's possible is that maybe having the touchdowns or something in here is enough to replace these guys, right? I don't know if that makes sense in this situation, right? But sometimes we can have a variable or a predictor that overshadows all of these guys. So then we can say, well, what if I can actually pull these out and simplify it, remembering that we always want to have the simplest model that we can possibly have. And so after we fit this huge model, we usually want to try to trim it down a little bit.
Yeah. But to start with, you have 5 factors, right?
Yeah.
5 factors. Then
Yeah.
how did he chose those 2 subsets? Or just say, yeah. Okay. Okay.
Points against, yards against.
Yes.
Mostly because it's reasonable to think that the points against would move with the yards against, right? And so they would be, and you could probably tie it back to the multicollinearity. I don't quite remember, actually. I think.
If you plot a scatter plot between those 2 point against the hard
Mhm.
if it's a linear scatter plot, can you say that they are related?
Yes, then you can say that they're related.
Points against versus that. If any sort of pattern, doesn't matter if it's a linear
Yeah.
or exponential.
Yeah,
If
then they're
any
related.
pattern,
Yeah.
If it is scattered, then they are not related in any.
That's right.
That's one way to choose you.
Yeah. And often it's just knowing something about the data. It's hard because I don't know anything about football, right? And I'm pretty sure it was the Super Bowl yesterday, but I'm not 100% certain.
No, what I'm thinking actually is for the process,
Mm-hmm.
how he arrived on those 2.
Mm.
That's where I'm kind of struggling.
Let's see if I can refresh my memory here. Because I feel like it was just kind of like, oh, well, it's reasonable to think.
Oh, yeah.
Points against, yards against, both have low BIFs.
So is it correct? He started with LM,
Yes.
then chose.
So here, I'll steal this in here so that we have it too. Because I don't see any. There's the points for has a really high variance inflation factor. And then I think because the TDs is high too, So it was points for points against, yards against. Yeah, that doesn't help us at all. So it's not based off of this. Yards for, yards against. I think it was just a matter of suspecting that they're related. I am looking at this little guy here, though. This insignificant one. And this one being insignificant with a high variance inflation factor. So maybe I wasn't too far off in them thinking that maybe the TDs could take over for the other two.
Yeah, it's just strange how it came up with the subset. Yeah, because
Yeah,
you need to, well, firstly you need to be knowledgeable with the,
exactly.
with the subject, but
Yeah, yeah.
But if you are not and only basing on statistical table, you should have some basis on this idea.
Yeah, and we'll develop that today.
Oh.
So we'll have other ways that we can do it. Remember, the nested F-test is only if you have a model within a model.
Yeah.
Right? And so it's a very particular case. And so sometimes I think if you've built a more complex model, like a complete second order model, I think just as a rule, you might have an idea of a simpler model that could maybe replace it. And so that's how the nested one comes about. So it's not, maybe not obvious how the nested one comes about, but it is a very special case, right, where it's nested inside a bigger model.
P-value specifies what is a null hypothesis.
So the p-value here for each individual one is if this is significantly different from 0, right? This coefficient is significantly different.
Acceptance not right.
We never accept anything. I don't know if closed.
Yeah.
You fail to reject. Yeah. Sorry, I know what you mean though. So here, yeah, so here we would say, well, there's not enough evidence to say that this is significantly different from 0.
Yes.
And then we can tie that back to the nested F-test, which says for a group, for a nested group here, which was what? I don't even remember what the points against and yards against.
Yes.
Them as a group, both having coefficients significantly different from 0.
So when you're saying individually, we can't just remove the variable.
We can, but if we're talking about nested F-tests, no, then we don't.
Here it is individually, right?
Yeah.
Just by saying that if I was doing the model, I would just remove yards first and TD, yes.
Yeah.
Just take away they are not adding any values. Just do the model with the rest of the field.
Yeah. These might have become insignificant because we added yards against, for example. Right? And so because there is this multicollinearity, right? So that's when we need to be aware of, okay, well, we need to have a look at these, but stay on the line, because we will talk about how do we remove variables or predictors, how do we add them in, what are some methods that we can use, right? So we're gonna get there. The nested F-test is a special case where you're trying to reduce your model from a complex one to a simpler one. Sold. Half happy. We can think on, I'll finish this sentence. So at least one of the predictors in the subset is contributing significantly to the model. Bless you. I would say, as a rule, if you're trying to figure out what your nested ones are, right, you could start, so if you've got this huge complete second order model, you could probably use your nested one as the full interaction model, right? Or if you don't have the complete second order model, because often we don't need to go that far, right, and we just need the interaction model, well, nested in the interaction model is just this 2 predictor multiple regression, right? And so then we can say, well, could I be just as well off with just these guys as with this one added on, right? So it's just a way of comparing the model fits.
So we've kept all the 5 factors in the example.
That's right.
And we are looking for p-value which is nearby to 0.
That's right.
And taking off the variables which are kind of nearby to 1.
Yeah, the points against and the yards against. How we pick those? We're not really. That's what we're. Yeah, that's not what we're. Or that's what we're not entirely sure of, how those were picked. I suspect it was knowledge about the data, right? Knowing that those 2 things would probably behave together. Maybe looking at the scatter plots. But like I said, it's a pretty specific special case example. So I'm going to move on to just the general picking models, picking the best predictors, different ways of doing that. So we'll leave this chapter 3. How about that? I wonder if it would let you use this ANOVA command of model 1, model 2 if they're not nested. That I don't know. It probably wouldn't make sense. I think it assumes one's nested in the other. Something to try. All right. I know, still not sold, I can tell, but it's going to be okay. We'll think on it a little bit more. How about that? Chapter 4 is just called Additional Topics in Regression, which is where they just throw a bunch of other stuff at you that's not worthy of a chapter, but important.
And you don't need to worry about the F, the test statistic, right? F equal to full model minus reduced model divided by number of predictors.
No, I would give you the output. So that's what it is in case you're curious. But for us here, we're just applying it. And so I would give you the output, which would be this one.
So F is obtained by that form.
That's right.
The 11.2. Okay.
Yeah.
So we don't need to worry about calculating.
No. Don't worry. Yeah, nasty.
That's my main
If you did, I would have to give you a formula sheet. I would never expect you to have that in your mind. What a waste. There's Google, guys. We don't need to memorize anything. So we just need to know that it exists. That's our biggest power, knowing that all these things exist. And then we can just find our way to them. Chapter 4 is like I said, the last chapter of regression that we're going to talk about. And it's the last chapter that we've got before our test next week. Don't worry. I know. You guys were happy that it was going to be before reading break. So I'll remind you that you were happy about that. So we are going to review on Monday, and then we've got the test on the Wednesday. I will give you a practice test. And if you're comfortable with all the topics and things that I'm getting you to think about on the practice test, you will do well on the test. Because I'm not out to get you in any way. There's a lot of material here. And so I am going to try to focus your attention on certain things. So don't try to outlast me. If I tell you to only focus on a few things, only focus on a few things. We can deal with the rest of them later. Right? And so, because I think it's so interesting. I'll tell people, especially in my intro courses, this is what's on the test. And then I get these weird late night texts saying, hey, how do I do this? I'm like, you don't need to know it. Yeah, but if I had to, no. Sometimes I refuse to answer. But it's for their own good. There's key things I want in your mind. So the last chapter is going to be all the little things that don't really deserve their own section, but we have to talk about. And so in the textbook, it says, you can go through these in any order. We'll just go through them in the order they're presented, but they are just additional topics, right? So they're not meant to flow anymore. So it might get a little bit weird, where it's like, here's a topic. But the first thing we're going to talk about is added variable plots. So again, we're going to focus on, can we remove this variable? What's happening with this variable? We don't want to rely on just the t-test, right, for the slope, or for the coefficient, which is the slope. Because if there's multicollinearity that we don't know about, right, then we know that things can be kind of skewed. And so we want to be able to say, yes, I can remove this predictor because I looked at the added variable plots and nothing was happening here. Right? And so let's talk about what these things are and why we use them. So I'm going to say to check a predictor, right? To check a predictor, meaning to see if it is truly significant to the model. Oops, truly significant to the model. Or truly insignificant, right? Could go either way, right? Before we remove something that has a high p-value, just because it has a high p-value, you might want to check the added variable plots just to see if it is truly insignificant, right? Or maybe because it's being overshadowed by another predictor, right? So maybe what I should do is truly significant or insignificant to the model. Clean that up a bit. Right? Depends on the situation. I added that because usually we want to remove things and we want to make sure that we actually can remove it. Is it truly insignificant? So what we do is we remove that predictor that we want to remove. So we do what we wanted to do, and we find the residuals. And so to make an added variable plot, step one is to remove the predictor, right, the one that we're interested in. Remove the predictor. I'll put in brackets of interest, but from now on, the predictor will be the one of interest. Remove the predictor and fit the model with the remaining predictors. And fit the model with the remaining predictors. Okay. This model is going to give you some residuals, right? So we'll call this resid 1. This model yields, let's call it resid 1. Kind of using the notation probably that you would use in your coding. So your first set of residuals is that model with the predictor removed that you wanted to remove. Those residuals are everything that aren't captured by that model. Right? And then here comes the weird part. Then you're going to use the predictor, right, the one that you want to remove, as the response, and then the other predictors as the predictors. So you're trying to model this guy, the one that you're trying to remove, with the remaining predictors. Weird, right? But what happens, right? What happens is that if we're thinking about the residuals here, the residuals from that weird model, right, is going to be everything that's left over that those other predictors aren't capturing, right, in the predictor that I want to remove. Right? If that's a lot, I might not want to remove that because it might be contributing to my model. And so here, so how do I write this? I'll use a capital the predictor, fine, of interest. Use the predictor as the response. And fit the model with the remaining predictors. So both of these models have the same set of predictors, right? The ones that I'm ideally keeping in my model, right? Assuming that everything goes well. And so here, this model yields resid 2, let's call it. And residuals, again, are everything that's not captured by those predictors, right? All that activity that's not captured by the predictors. So then the actual added variable plot is the residuals from the second model against the residuals from the first model. Okay. So now the third step is to plot resid 2 against resid 1. Oh, so pleasant. That sounds really nice to wake up to, actually. Do, 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 do. Do, 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 do.
That's the issue.
Well, maybe if it's 10:30, might be able to wake up. Yeah, but if that's going off at 4 in the morning, yeah, I'd probably sleep through it. So now we're gonna plot on the y-axis, we're gonna have resid 2 against our x-axis, resid 1. And so now you've got the residuals against the residuals, and what you're gonna look for, right, if there's some sort of pattern, what that's telling you is that the predictor that you removed is adding something to the model, right? There's something unique in that predictor that's not being captured by the model without it. Okay. And so I'll kind of denote that by, let's say, a linear relationship. It's the easiest thing to think of. And I'll put it here in kind of my note color. A relationship can be positive, negative, linear, whatever, right? So a relationship means there is a unique not a unique, sorry, is unique. I skipped ahead. There is unique in the removed predictor. Okay. So if you're seeing this, right, what does that mean? Well, it means that we shouldn't remove this predictor. Okay. So therefore, we should not remove this predictor. That's added variable plots. It's just one thing that you can use if you are not sure if you should be removing it or not. And then, of course, if you have residuals 2 against residual 1s, then this line, right, this line would be resid 2 hat equals some b naught plus beta 1 resid 1. Right, a simple linear regression. You can test the slope if it's significantly different from 0. If it's not oh, okay. Huh. If it's not significantly different from 0, then there's no relationship. Can test this simple linear regression, SLR. to see if beta 1 equals 0 is RH naught. Essentially, is the slope significantly different from 0, which is exactly what we're doing for these multiple coefficients as well, right? So we haven't done anything to it. Right now, we're just back to the simple linear regression case. So we've just got the one predictor. And so it's just another way to see, okay, well, or to argue, yes, I can remove this, or no, I cannot remove this. It has to be in my model. Right? It is assuming, right, that we keep these set of predictors, right? If I want to change the other set of predictors, fine, I have to keep that one in there. What if I remove this one? Then I have to redo it all, right? But that's just a matter of copying and pasting your code or whatever, right? So it's not hard. Just need to keep track of your code. And so you can do it, but there are more elegant ways of figuring out if you should remove it or not, remove a predictor or not. Any questions, though, before we go on to that? No? Okay. So, section 4.2 is called Techniques for Choosing Predictors. Now, there's lots, of course, like everything, there's lots of ways to do the same thing because you have to remember all these people needed PhDs. So, I mean, you have to come up with something. Like, I do want to read that, but anyways. Right, so all these different techniques, what you just need to remember is, okay, well, it's not that one is necessarily better than the other. We just need to be exposed to all these different techniques because people have come up with them along the way. It might have been particular to their case, right? Might have been particular to their grad studies. I have to crank out a PhD. What am I supposed to do? Things like, so pretty obvious things like, if I'm choosing from a set of predictors, what if I just build a model with all of them in there, right? And then slowly, I remove the ones with the largest p-values, right? And so what that's called is it's called backward elimination, right? And so you're fitting the full model, everything that you could possibly want in there, and then slowly but surely, you take away the one with the largest p-value, for example, and then you fit the model again, pull out the one with the largest p-value, fit the model again, pull out the one with the largest. Of course, we don't do this by hand anymore. R just does it for us, right? Or another technique that we could use is we start with no predictors. We look at the correlations, which one has the highest correlation with my response variable. I put that in. Right? Is it significant? Great, I keep going. And then I find the next highest correlation with my response, put it into my model, right? And that's kind of how I think how we default to building models, right? Is we build a simple one and then we tack on another thing. If that's still significant, then I go and find another thing and I put it into my model. And then I keep going, keep going, keep going. What we've seen a little bit is, that's a more efficient alarm, probably. What we've seen a little bit is that we could have a model, right? And the simpler model, all those predictors are significant, right? But then if we add in another one, right, probably one that's correlated with the others, then that one becomes significant and then the other ones aren't significant anymore, right? We saw that in the housing one, which I'm a little bit too lazy to go grab because it's just a quick example, but right, and so then some of these predictors are going to be insignificant because the newest one was more significant, and so it's kind of taking over. And so I think it's called, what is it? Forward selection. So we talked about backward elimination, forward selection, and then there's this kind of like dance one where we're doing stepwise. So we start with the forward selection. So we start with nothing, we put it in, make sure it's significant, move on. And then as soon as we hit where we get to the point where one is maybe insignificant, but it's not the most recent one, then we apply backward elimination so that we're left with this more simplest, or the simplest model that we can have, right? With still all significant predictors.
Is there a logic or an order of what to add next or what to eliminate?
If you're starting from nothing,
Yeah.
you would look at the correlations.
Correlation, the
Yeah.
highest value to the
Yeah.
lowest value. Something like that.
Exactly. And that's how you would put them in.
Then for the removal.
And then for the removal, then you look at the p-values,
p-value.
and then it'll pull out the ones with the insignificant p-values, or the most insignificant p-values. But it'll do it at every step because everything's changing at every step.
Yeah.
Right?
Sure.
And so, so those are the kind of the three main players. Of course, R does all of them just for you, right? So it's more about knowing what it's doing, interpreting the results. Okay. So, about, well, I should preface it. There are many techniques for choosing predictors. So there are many techniques for selecting predictors in our model. Let's say that. We talked about backward elimination. Is one of them. Where we start with the full model, so all the predictors that are under consideration, whether that's a complete second order model, right, with the squares and with the interaction terms, whatever. It's going to be easier to think about just plain old predictors. But in any case, we start with the full model. Which has all the terms under consideration. Let's do it as kind of a step-by-step approach. So step one, we start with the full model. So you throw them all in there, see what happens. And then the next step is to remove the single predictor with the highest p-value. Remove the predictor with the largest p-value. Right. I am assuming that it's insignificant, right? Largest p-value over 0.05. If all of these are significant, then there's nothing to remove. Assuming p-value, assuming the p-value is insignificant. Refit the model and repeat. Refit the model. Oops. And repeat. So you just keep going. I guess I should say repeat until all predictors are significant. Until all predictors are significant.
So this is the one way of doing it. Just
That's right.
What about the coefficient values?
Just based off of the coefficients translate into the p-values, and so we'll focus more on the p-values. I'm sure someone has written a paper somewhere using just the coefficients, but we're going to focus on the p-values, right? Because that's what R does. If we tell it to do backward elimination, it'll just go, and so we give it all the possible predictors. Hey, have a look at these, and then it just does it for us, right? And it'll just go based off of the p-values less than 0.05, greater than 0.05 in this case. Right. I'm sure someone somewhere has done it using other things, but we're going to use the p-values. Okay, so that was backward elimination. And then I want to call it the right name, forward selection. Yeah. So then the other option is forward selection. Also pretty common. So forward selection is where step one, we start with no predictors, right? And then just use the predictor with the largest correlation with the response. So start essentially with no predictors, That's not going to do anything, right? You have no predictors, so that's not really a model. But just to clarify that you're starting from the full model or you're starting from nothing, right? Here we're starting from nothing and we're building it up. And so start with no predictors, and then add the predictor with the highest correlation. Oops. With the highest correlation with the response variable. With the response variable. If the p-value of that predictor is significant, then you add the next predictor. So if the p-value of that predictor is significant, then we add the next predictor. Then we add the next predictor and again, of course, it's based off of correlation again. Based off of correlation. We continue, right? We continue this way. So then we refit the model with that predictor in there. If it's significant, then we go on to the next one, and then we go on to the next one, and then until we hit something that's insignificant, right? That one does not go in the model, and then we're done. So then we continue until the newest predictor added is not significant. The insignificant predictor is not kept in the model. The insignificant predictor is not kept in the model. Oops. Right, then we stop.
So let's say we have done the first prediction and we got a significant p-value.
Yep.
We've added that to the model. We've taken the second one, tagged or done separately and then tagged along with this.
Yep.
We have run it and we have seen the second one is not that significant
Mm-hmm.
when we have done it individually, but if you're grouping it on estimate,
Yeah.
it's not that significant. So in that instance, what are we going to do?
It's how it behaves in the model that it's in, right? So we're assuming that the one that's made it into the model from step 2, right, or from step 3, right? So there we added a predictor. It's in there now,
Okay.
right? So then in the next step we're adding it onto there. If it turns out that that's significant, we keep it. If it's not significant, we stop and we don't keep it.
Okay. So it's like if you have 4 variables with one predictor, so it's like 1, and we are accumulating this but not doing individually, right?
That's right. So we're always just adding on. Yeah.
If we find significant, then we finalize it and again go for
Yeah.
the third one.
That's right.
Or else leave it
And then you just keep going until you find one that's not significant, right? Based off of the correlations with the response.
Is there a case where when you added a new variable, the ones that are already in the model became insignificant?
That's right. Yeah. Sometimes that will happen, right? Because a newer variable is going to be more powerful than the variables in there. So that's our last option, is the stepwise elimination, right? Where we do forward selection, right? Where we start with nothing and we're building on, but then at each interval, so at each model, we check in to say, hey, are there any insignificant ones? If so, I'm going to remove those, right? As long as I keep getting significant ones as my most recent one, I'm going to remove through backward elimination. I'm going to pull out the ones that are turning insignificant, right? Just kind of getting them out of there so that I'm left with only significant terms again, right? So that's our third option, which is kind of like a combo of the first two.
Do you keep that insignificant variable till the end or just remove it then and then?
Yeah, so I was taught that it had to get bumped to the end
And then
removed it. They don't emphasize that, so maybe my supervisor is just really old school.
again, if you're doing that again, it's a kind of
It would be
backward.
another kind of step. I'm sure it has a special name. like a special kind of stepwise regression. So let's talk about the stepwise regression. So stepwise regression is we start with forward selection. Start with forward selection. After fitting each model, right, we would use backward elimination on any of the insignificant terms. Right? So after fitting each model, we perform backward elimination on any insignificant predictors. On any insignificant predictors.
You rank it? I mean, you're on the third step, right? So the third variable. So
yeah,
then one of the first two variables became insignificant.
That's right.
Now, let's say one p-value is 0.1 and the other p-value is 0.2.
Yeah, so I would have to do it twice. So it would start with the forward selection. So let's say we're at 3 variables, right? The last one is now significant, but the first 2 are now insignificant, right? It would pull out the one with the largest p-value. We would fit the model again. Oh, that's hard. We would fit the model again, right? Making sure that this one is still significant. If this one is still insignificant, we would pull it out as well, right? So we would do 2 steps backward and then make sure that this one's still significant.
So you really retain the variable that is significant.
Is significant. So here, what can be a problem is that we end up with a model with only significant predictors, right? Which might actually not get us the highest R squared, right? And so sometimes there's a trade-off. Whereas if we're thinking about, well, the backward elimination, we end up with all significant predictors, right? Because we're thinning the herd, right, until we have only significant predictors. So backward selection and stepwise regression, we get only significant predictors, right? Whereas forward selection, we might end up with some insignificant predictors, but depending on the situation, maybe that's a better model, right? Maybe that's a stronger model. So it depends on the situation, but all of these are going to give you probably slightly different models, just depending on how we arrange things, right? And how they're added into, because the stepwise regression doesn't necessarily give you the same thing as the backward elimination, right? Because we're adding things in different orders, and then we're taking them out, right, as we're going. So, so that's something to keep in mind too, that they don't necessarily give you the same models. So that's worth comparing too, right? Use each of these 3 main players, compare those models to see which one is best. Let me finish this list here. Oh shoot, I'm really out of time. Sorry guys. Just blah, 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 blah. Model will have only significant predictors. I think that's what I wanted to say either way. talk some more about it next day. Any questions though? No? All right. Like I said, so the lab is, we're just gonna use that time for you guys to work on lab 2 and assignment 1, right? Kind of wrap up. We'll work on some new lab stuff next week. How about? I feel like you guys have a lot going on. Yeah, it's completely, if you're all done, then yeah.
So,
it's your time to use.
can I continue to be like more and then have only significant predictors in the end or in the end?
Yeah. I'll say final model.
Yeah.
How's that? Like, good.
Yeah, I should